Bad? Very good? So the food has been very good then? Oh, the food has been so-so and the presentation has been good? Or the food has been good and the presentation has been good? Both. Oh yeah, that's good. Takes a while for my system to boot. I need to get a new system. It's starting to get old. It's about 3 years old. So. Well, I can sort of start a little bit ahead of time while I wait for my system to boot. So even though I don't have any slides right now. So what I'm going to talk about is developing in a multi-core world. So how do we as a developer survive in a world that our systems are getting more and more cores, right? And what can we as an operating system do to help you? So we have a lot of talks done by our compiler people about how to use compilers, how you write OpenMP code, how you use auto-pair of the compiler and so on and so forth. And that's all good and nice, but that tells you the half part of the story. The other part of the story is more of what can we as an operating system do to assist you, to make your life easier. And what are some of the design choices, right? I know like most of us, we don't start with a clean slate of paper. We have a legacy application that we now need to move from a single core world into multi-core world, right? And most people say like, okay, tear it apart, write multi-threaded code of it, right? That's kind of the usual answer you get. And that is true if you want to get absolute maximum scalability. Then you need to write multi-threaded code in one way or another. The best way sort of for a developer perspective is actually to use something in OpenMP, because then you use, rather than to manage threads yourself, you declare the usage of variables. And then the compiler can use those declarations to make intelligent decisions on whether or not that loop or that part of code can be parallelized. So that's the sort of the easier way for a developer to get somewhat scalability, right? But that scalability you get from a OpenMP kind of flats out about 24 CPUs. But 16 to 24 CPUs, somewhere around there, you have fairly good scalability for a 12 CPUs. Then you're starting to see fairly like the return is getting less and less and less, right? So if you want to even get a better scalability, then you need to write multi-threaded code. But it's hard to take the big piece of code that I have and then multi-thread it, right? It's pretty hard. So there are actually other ways we can do, there's other things we can do to sort of simplify the way we are using code. We probably have to rewrite and redesign our application slightly. But I found out that I'm a die-hard Unix developer and Unix user. So I'm living and dying by do one thing and do it well. And then you have many processes, many tasks that works together to build a solution. In Unix, when we use the shell, we use the pipe, right? You're building things pipe. And I tend to build those applications. I used to tend to build applications that way as well. I might use pipes for my application. I might maybe use a socket or something to do communication. But I usually build many modules that I then can plug together to get a stream to process the data. And it turns out that if I write my application, if I have application that is written that way, I can then look at the data that I have. And I can usually partition the data horizontally and go from a single stream that I used to have before on my single CPU onto multiple streams and actually get a fairly decent scalability. It won't scale as well as I do in a multi-threaded code, but they actually give you fairly decent scalability. So these are some of the things that, okay, let's see, I can actually log in now. So continue. So that's some part of the things that we can do. And then what I'm going to talk more about is then the facilities that we have in the operating system if you then need to go and do multi-threaded code, right? Multi-threaded code is hard. It's really, really hard. So we have facilities in the operating system to help you to take some of the hard tasks out of your life so that you don't have to do them yourselves. So we can deal with the hard stuff. You can think about your application and your application logic, and you can leave things like signal handling and things like that, asynchronous handling and things like that to us by changing the APIs that you use slightly. Thinking about how you use locking and things like that. We can deal with the stuff. You deal with your application logic, and you leave the gory details to us more than for you. But then if you're writing multi-threaded code, you have to understand how the threads model works. I'm also going to go through how the threads model work. So the things that I'm going to talk about a little bit today, I'm going to talk about the threads model. I'm going to talk about something called event ports. I'm going to talk about a replacement for the normal libc malloc. We have a number of malloc implementations in OpenSolaris or in Solaris that you can use for different versions, different things. And the good thing with them, if you just use the standard APIs, they just plug in, they're plug compatible. You just either use the preload or you link to a different library. You don't have to change any code. But then some of those also have specific extensions that you can use to get even better scalability to your applications. I'm going to talk a little bit about those things as well. So now it should work. Yeah, thank you. Have you been able to check out yet? Yeah. I haven't even had lunch. Come on. So there we are. Can I get my slides up? So, develop in a multi-core world. So the things, I will skip the introduction. So what are your new challenges? So things are changing, and what you see today are kind of the beginning, right? I have in my laptop a dual core CPU, so my laptop is a dual core machine. If you look at AMD's latest CPUs, they have 12 cores. If you take a 4-socket machine of those, put together, you get 48 cores. Intel have 8-core CPUs with hyper-threading on them, so that for an application that actually looks like 16 CPUs. And you put 4 cores in that, then you have 96 core. You have 96 CPUs to deal with. And the way a lot of people have been writing code previously, it ain't working, because we've been spoiled by getting faster and faster CPUs, and we've been basically writing bad code, and faster CPUs and bigger memory kind of solve that problem for us. That's history. You guys, you're gonna have to start earning your money now. You got to learn how to write good code. Some architecture choices we can make, some good rules to follow, and then what we Solaris can do. Basically, that's what an operating system is there for, right? We are there to facilitate for applications to run to virtualize resources, to make things easier for applications, right? That's why I have an operating system. If we can't do that, then we don't have any right to exist. So that's what we need to do. So the world is changing. Classically, we have CPU speed, execution optimization, and cache. We basically get faster and faster CPUs. One of the things that happens here is that the difference between my clock speed and my memory speed is going up. So while spending more and more time not doing anything because I'm waiting for memory. That is what, for example, we are using in the UltraSpark T series. We're basically using these windows when one thread is waiting for memory to come. We then have multiple hardware contexts in each CPU. So each of these cores can then run multiple hardware, what we call hardware threads, and we're basically switching them very, very efficiently. And for the application, they don't notice that we're running another thread while you're waiting for memory, because you're waiting for memory anyway. So the CPU, if you didn't do that, you would only stand there and do null operations. So what happened when we increased clock speed was that we got more and more heat dissipation and took more and more power. So we get less and less return for the money, right? The faster we went, it was harder and harder. And it turned out to be, the limit seems to be, with current technology, seems to be around 3-4 gigahertz. If you go up over there, you're just getting more heat, so you become a good tea cooker. You become a very, very good teapot, but you don't get much work done. So what we see now is that people, instead of spending the CPU counts and getting a bit faster CPUs and things like that, and spending the transistor count for that, they're spending transistor counts on putting more cores, functional units in the same CPU. And we'll see two different sides of it. One of them are actually putting very, very fast cores, but fewer cores on the 4, maybe 6, maybe 8 cores on a die. Then we have the other end of the spectrum where we have the UltraSpark T CPU, and there's even others like the Azure and other CPUs that putting even larger number of CPUs in one core, but each of the CPU is not the fastest CPU in the world. But it doesn't have to be that, but it's not designed to do single-threaded performance. It's designed to do throughput. So if we look at a CPU that it has an amazing I/O capability, because it has to drive a lot of I/O traffic, both on networking and on memory. So application consideration changes. Application performance will be driven more by throughput than single-threaded performance. So we have to think about how can I change the way of looking at application from basically looking at a single stream of data to multiple streams of data. Things like web applications tend to scale very well in this, because they are by default have multiple streams of data coming in. But there are then you have the web server, you have the database, and those also have to be adopted to deal with these multiple streams of data coming in, and you have to be able to process these multiple streams very quickly. So efficient use of exploit pilots. So we're doing things. So this is kind of the extreme of the extremes. This is our UltraSpark T3 CPU, which comes out later on this year. It has 16 cores. Each core have 8 hardware threads. So that is for each CPU have 128 virtual execution units. So how many of you have ever run a program on an SMP system with 128 CPUs? That used to be a very, very large box. We made those boxes in the late 90s. Those were big boxes. Now it's a chip. And we can put 4 of these chips together. You put 4 of these, you have a 512 ways SMP system in a 4U box. What do you do with that? Which means that we have to completely rethink how we deal with system. And it's both for us as developers, but also if you look at how you do deployment, right? So that's why you see this wave of virtualization hitting the industry right now, because that's one way of being able to utilize these boxes is to sort of break it up into smaller boxes. The other way of utilizing is to realize that the best way of writing like complex software is actually to have an SMP system where they have a uniform memory model rather than to having a cluster where you have everything split out in different ways and you have to deal with data partitioning and data location and you just go crazy. If you have an SMP with a lot of memory, well, its data is in the memory. Where it's in the memory, I don't care. It's in the memory. So these things get very, very hard. And one of the things we are doing one of the things we need to do here is we need to help you there. And we can do that because we have been in this business for a long time. As I said, we did 128-way systems in the late 90s. We actually had projects then to be able to put these boxes together and to go up to thousands of CPUs in one single image. That never got into fruition, but we're seeing those systems coming up now by multi-core systems rather than discrete CPUs. So we've been in the business of writing an operating system to run on these type of systems for the last 10 years, almost 20 years. Basically, we've been there, we've done it. This is something we actually, Solaris is really, really, really good at this. Because we had to do it, otherwise we wouldn't have survived to sell our servers. So, what's on the menu? Basically, you have you can architecture choice. So, I call them big and fat and small and nimble. Big and fat is basically you create these big blocks of multi-threaded code. Big processes, many threads in each process, large memory space inside one process. The other, and the pros here is that if you do it right, it scales really, really well. But the caveat is like, it's hard. It's damn hard. Writing threaded code, writing scalable code is really, really tough. The other way of doing things is what I call small and nimble. It's kind of the art of Unix programming, the standard way we in the Unix world have been writing programs a long time. And if you do that right, if you do that in a decent way, you partition your data, you can actually create multiple streams in user space with separate processes rather than separate threads that actually runs fairly well. And coming back to one of the advantages of that is it's easy to do that. So it's easier, so you let the operating system deal with the hard stuff. The key place where you should think about using something like that is when you have to retrofit old code. So if you have an existing code base. If you're starting from a clean slate of paper, use a multi-threaded model. It will scale better for the long run. Sooner or later, even if you're maintaining an old code base, you will have to go that path, right? But if you have an old code base and you want to be able to utilize new multi-core systems, maybe you can't wait on redesigning your application and rewrite your application, because that is what you have to do to get really, really good scalability. But to get decent scalability, you can do a number of small, quick tricks to get started. The bad part, it doesn't scale. It scales, but doesn't scale that well. It scales maybe 4, 8, maybe up to 16 CPUs. I've seen a couple of applications that we've driven up to like 32 CPUs in kind of using that type of architecture. But that was a very, very specific thing where we were able to partition the data very, very nicely, and then we had just pipes of sort of processing units that they just read the data in an incoming pipe and processed it and then sent it out on the outgoing pipe and then take the next data, and it was just very, very easy application to sort of streamline. And the key there was that we changed the application a little bit so that it could deal with that the data was partitioned, and they knew that I was going to go get my part of the data from there, and another stream took its part of data there, and we put basically in front of that, we had a small multi-thread application that basically sorted the data into different piles, and then we had single-threaded streams that was dealing with the different piles of data. And that's very trivial, but in this case, it was a telco mitigation software. It just read telco billing data, did the transformation of the format of the billing data, and there were different stages doing different format information. We could build up a nice pipe, just send the data through the pipe, and it was easy. Most applications might not, a lot of applications might not be that easy, but that's a way to do it. And anywhere you go, the operating system, you need an operating system that can help you, that actually will scale onto these CPU, these large number of CPUs. And that is what Solaris is really, really good at. It scales up to these CPUs. So if you run other operating systems, you might have to partition your system into maybe 8 or 16 cores per execution units per system, because the operating system doesn't scale above that. Basically, the services you have an operating system, they don't scale past that amount of CPUs. So, big and fat, it's empty program one way or another. POSIX threads, it's the hardest way of doing things, but it's the potential best scalability. You control the program flow, you control the data, so you control concurrency. It's hardest, but it gives best potential scalability. But it also requires you to have really good programmers, because this is really easy to mess up. The next way is using something like OpenMP, where you declare the usage of data. So you declare how this data is going to be private, this data is going to be shared, and so on and so forth. And then the compiler can use those directives to decide, okay, I can parallelize this piece of code. I can parallelize this actually, what actually turns out to be a big loop, but if you look at the code first, you kind of just look at the sequential piece of code, but I can actually turn it into a loop, and I can parallelize that. And it can do a lot of things if it knows how you're going to use your data. Otherwise, we have also an automatic parallelize, or we have our compilers can also automatically parallelize the code. But it will only do it on loops, because it doesn't have a clue about how you're going to use the data. So if it's not sure that, okay, this is definitely data is not going to be used anywhere else, it's not going to be shared use of this data, then just, okay, I can't touch that. I don't know how data is going to be used here, so hands off. Then VM-based languages, the virtual machine-based language, where part of the hard pieces of dealing with threading and things like that is put into the virtual machine. So the virtual machine is doing part of the gory details for you. And that's the most popular language there is Java, but probably actually one of the better languages for writing multi-threaded code is actually Erlang. It writes very, very nice code. So in that case, the compiler and the virtual machine deals with a lot of the details, and the language usually have built-in support in it directly for multi-threads. And modern languages like Java have concurrency primitives and things like built into the language itself. Whereas in C++, that's something that's kind of been, well, let's see here, can we just squeeze it in there in the corner over there? And yeah, well, kind of fits a little bit, but not really well. So it's not, C and C++ was not designed with concurrency in mind, so there's no, the C language doesn't understand that. If you want to look at the really, really nice language, if you're doing mathematical stuff, you should look at Erlang. Really, really nice. No, not Erlang, Fortran. It's a kind of the next generation of Fortran. You basically write the code in mathematical statements. And the whole language is based around multi-threading, so it's just in the language. You don't even have to think about it. Really, really cool language, actually. Small and nimble. So many cooperating programs. Sounds familiar for those of you. So many of you are old-time Unix users. So anybody going back to 82? That's how old Unix user I am. I got my first Sun workstation in '85. So that's basically a good old Unix programming. Like there's a very, very good book called The Art of Unix Programming. It's a very, very nice book. You do one thing, you do it well. communicate with well-known interfaces, pipes, sockets, and other things, right? You do one thing, you communicate with well-defined, simple interfaces. Okay, that's no. So the way you can use this for getting scalability is retrofit old code. That's where it fits, right? If you start from scratch, you start from scratch and you do things new, right? But if you have old code and you want to get it to scale reasonably, you can usually do fairly small design changes in the edges of the software. Because most of the times, these pieces of software are designed to manipulate a single stream of data. And that data, if you start looking at the data, it's very, very often that you can do horizontal partitioning of the data itself. But that means that you need to put something in the front and the back to sort of do the horizontal partitioning of the data and then do the correlation of the data in the end, right? But because in this old single-threaded code, you don't have any concurrency features in that path. So you need to see to that you don't have to synchronize two data flows with each other until the end of the processing. If you have data flows that are depending on each other, then you might have to do a little bit design to actually do how you process the data flow. Rewrite code for multi-threading will scale better, but it will be harder. It will longer time to market. So it means that you will be passed by the company that took the decision to do it the simple way. So the best example of this in the industry is Sybase and Oracle. This goes back to the 92, 93 sometime, right? Back in 92, 93, on the Sun system, Sybase was ruling the world. They were screaming on our machine stand, but they were single-threaded. And Oracle's database, they were also single-threaded. So Oracle basically, they rewrote their database and made it multi-threaded and multi-process. And when we came out with our SMP systems in 94, 95, Oracle didn't stand a chance. No, Sybase didn't stand a chance against Oracle. Because Oracle databases then scaled up to our SMP systems. Whereas Sybase database at that point in time, they were basically locked onto sort of what you could get out of one CPU. That's kind of, if you go into history, and that's the choice they made. They made a choice actually to do a complete, this time they actually did a complete rewrite to write a fully threaded one big process model. Whereas Oracle kind of took the hybrid way of kind of, okay, I can do multi-threading parts and I can kind of do multi-processes as well to get scalability, right? Rather than having one big multi-threaded server. And when Sybase came out with their multi-threaded server, the trains left the station. It was like, bye-bye. And you can see the size of the two companies, right? So it's time to market and keeping you on the market and keeping you sort of, keeping you on the cutting line is an important thing. So one of the questions I've gotten when I've been talking to developers and sort of when we sort of throwing out ideas. So that means that we have to create a lot of new processes, short-lived processes, and that's expensive, right? Well, it turns out that with both improvements in operating system and in processes, it's actually not that expensive anymore to create processes. So it turns out that the cost of that has gone down fairly drastically. It's actually not that bad. It is a lot more expensive than creating threads, but it's not that bad as that used to be. So it used to be pretty bad, now it's not that bad, but it's getting better. So hybrid, which is kind of the middle way. So you multi-thread part of your old code, and you still use multiple processes, and which is kind of the model that you usually see what people ending up with when they try to retrofit old code to scale on a multi-core system, right? So look at your application logic and see what things that are, where can I do multi-thread? Where can I multi-thread my code without having to do too much re-architecture of the design. So I don't have to redesign. I don't have to like throw everything away. I can reuse the most part of the code, but I kind of look at where are my hotspots in my application, and I kind of focus on those parts to create an application that scales, that at least starting to scale on a multi-core system. So grab the low-hanging fruits first, and one way you can actually start looking at this, actually using compilers like the Karlsson Studio compilers, that you can just tell it to do ---- autopar, and it will try to find loops in your code and parallelize it yourself. It will scale reasonably to like 4 or 6 CPUs, something like that, and it's a good start. It will look for nested loops. Non-loop code will just be, okay, this is not a loop, I don't do that. So it's a start of getting parallelization, but